The figure below shows an I-beam section. An I-beam section is a beam whose cross section is in the shape of an I, letter I. Now, the questions about this beam are as follows. Determine the maximum bending moment that should be imposed on this section if the tensile stress in the top flange is not to exceed 40 meganewtons per square millimeters. So this is what we are referring to as the top flange, and in this top flange the maximum tensile stress should not exceed 40 meganewtons per square meter. The second part of the question, what is then the value of the compressive stress in the bottom flange? The bottom flange is this lower section. We call it the bottom flange. Now the middle section, we call it the web. Now, the first thing we are going to do is to determine the position of the center of gravity of this I-beam section. And for us to determine the position of the center of gravity, we are going to use a table that looks like this, whereby we are going to have the component, and our components are the top flange, the web, as well as the bottom flange. The next part is to determine the area of each component. For example, the area of the top flange is going to be the breadth of 200 millimeters. Therefore, we have breadth of 200 millimeters times a depth of 40 millimeters, which is going to give us 8,000 square millimeters. Therefore, that is the area of the top flange. The area of the web is going to be a breadth of 40 millimeters times a depth of 200 millimeters, which is also going to be 8,000 as well. And then the area of the bottom flange is going to be breadth of 120 millimeters, therefore 120 millimeters multiplied by a depth of 40 millimeters, which is going to be 4,800 square millimeters. Therefore, those are the areas of all the three components. The next thing is to locate the center of gravity of each of these three components, and that's what we are calling centroidal distance y from LL. LL is this section here on the bottom flange. Now, the centroidal distance y from LL of the top flange is going to be the distance from LL all the way to the center of gravity of the top flange. Now, in our last lesson, we saw how we should determine the position of the center of gravity of a rectangular section. We do that by doing, by joining the diagonals. So join the diagonals of the rectangular section, and where the diagonals meet, that becomes the center of gravity of that rectangular section. Therefore, this is the center of gravity. Center of gravity is usually denoted by letter G. Therefore, this is the center of gravity of the top flange. The center of gravity of the web, we also determine it by joining the diagonals. They are meeting at that point, and therefore that becomes the center of gravity of the web. For the bottom flange, we also join the diagonals. Where are they meeting? They are meeting at that point. They are meeting at this point, and therefore this becomes the center of gravity of the bottom flange. Now, the centroidal distance y from LL of the top flange is going to be the distance from LL all the way up to this center of gravity of the top flange, which is going to be 40 millimeters plus 200, that is 240, plus half of this depth, which is 20. So that is 240 plus 20, 260. Therefore, the centroidal distance y from LL of the top flange is 260 millimeters. For the web, it is going to be 40 plus 100, that is half of 200. So that is going to be 140 millimeters. For the bottom flange, is going to be half the depth, which is 40 divided by 2, that is 20. Now, the next section of this table that we are going to fill is we take the area of each component, we multiply by its centroidal distance y, and that is going to give us AY. A times centroidal distance y from LL. Now, for the top flange, we have 8,000 times 260, which is going to give us 20,080,000. That means 2,080,000. For the web, 8,000 times 140, that is going to give us 112, 1, 2, 3, 4. That is 1,120,000. For the bottom flange, 4,800 times 20, that is going to be 96,000. Therefore, we got 96,000. So, those are the values of AY. So, when we add, we are going to have 0, 0, 0, 6, 17, 18, 19, 9, 2, 3. So that is going to be 3,296,000. So that is summation of AY. Then we add the areas of the three components, which is going to be, that is 8, then 16, 20. Therefore, 20,800 square millimeters. Now, for us to get the center of gravity of now the whole I-beam section, we are going to say this. Bar Y is going to be given by summation of AY all over summation of A. That is the sum of AY divided by the sum of areas. So that is going to be 3,296,000. Divide this by 20,800. So when you divide the two figures, the two values, you are going to have 158.5 millimeters. Therefore, that is the value of bar Y. Now, when we try to locate it on this I-beam section, we have the whole of this section from LL up to this point being 200 and 240. This center here, the center of gravity of the web is 100 and 140. So 158.5 from 140 that point. So this becomes the center of gravity of this I-beam section. So that is G. Center of gravity of this I-beam section. Now, at the center of gravity of this I-beam section, that is where the neutral axis passes. Neutral axis. And that means that at this layer, or at this section here, the beam is not subjected to any form of stress. That's why that section we call it neutral axis. Now, when you try to plot a stress distribution diagram for this I-beam section, it is going to be in this form. That is the center of gravity, or the neutral axis. Yep. So this is a stress distribution diagram whereby at this point we have the maximum tensile stress, and at this section here, or at this point, we have maximum compressive stress. And at the neutral axis we have zero stress. There is no stress. Therefore, stress increases downwards from the center of gravity and also increases upwards from the center of gravity. The top fiber is subjected to tensile stress and the bottom fiber is subjected to compressive stress. And that's why the question is telling us somewhere that in the top flange, the tensile stress should not exceed 40 meganewtons per square millimeter. Therefore, it means that the maximum tensile stress that the top flange should be subjected to should not exceed 40 meganewtons per square millimeter. We are also asked to determine the value of the compressive stress in the bottom fiber. The bottom flange, the bottom flange is subjected to compressive stress, and this bottom fiber here is subjected to the maximum compressive stress. Now, after determining the position of the center of gravity of this I-beam section, we are going to light the 158.5 millimeters, whereby that 158.5 millimeters, we call it YC. The reason being, that is a section that is subjected to compressive stress. Now, the section above the neutral axis, that section we call it YT, and it is the section that is subjected to tensile stress. Therefore, when we subtract 158.5 from the depth of this I-beam section, which is 40 plus 200, 240, 240 plus 40, that is 280. Therefore, 280 minus 158.5 is going to be 121.5 millimeters. Therefore, that is the section that is subjected to tensile stress. So we call it YT. Now, the next thing we are going to do is to calculate the value of the moment of inertia about the x-axis, or in other words, about the neutral axis. So the neutral axis is along the x-axis. Now, for us to get the value of moment of inertia about the x-axis or the neutral axis, we are going to calculate the center of, the moment of inertia of the top flange about the neutral axis. We add that to the moment of inertia of the web about the neutral axis, and we also add that to the moment of inertia of the bottom flange about the same neutral axis. Now, the moment of inertia of the top flange, that is TF, about the neutral axis, is going to be given by BD cubed divided by 12. That is how to determine the moment of inertia of a rectangular section. Then we add the area of the top flange. We multiply that by the segmental strip, that is the distance from center of gravity of this I-beam section up to the center of gravity of the top flange. So that's going to be given by, that is going to be YT minus Y, and then we square. So that is going to be YT minus Y, and then we square that. So this is going to be the breadth of the top flange is 200 millimeters. Therefore, we are going to have 200 millimeters multiplied by the depth of the top flange is 40 millimeters. Therefore, times 40 cubed all over 12 plus the area of the top flange, 8,000 square millimeters. Therefore, plus 8,000 into YT is 121.5. Therefore, 121.5 minus 20, distance from this top fiber here up to the center of gravity of the top flange. So that is going to be minus 20, and then we square it in that form. Now, when we carry out that calculation, we are going to have the moment of inertia of the top flange being 83,484,667 millimeters raised to the power of 4. Therefore, that is the moment of inertia of the top flange about the neutral axis. From there, we determine the moment of inertia of the web about the neutral axis, which is also a rectangle. Therefore, BD cubed over 12 plus area of the web into. So, for us to get the distance from GW to G, that is going to be G, which is YC. Therefore, we have YC minus GW, the distance from LL is 140, and that is Y. And then we square that. So this is going to be, the breadth of the web is 40 millimeters. The depth of the web is 200 millimeters. We cube it. We divide this by 12. We add the area of the web, which is 8,000 square millimeters, and then YC is 158.5. Therefore, 158.5 minus Y is 140, and then we square that. Now, when we use a calculator to determine the value of that, we are going to have the moment of inertia of the web about the neutral axis being 29,484,667 404,667 millimeters raised to the power of 4. So that is the moment of inertia of the web about the neutral axis. Finally, the moment of inertia of the bottom flange about the neutral axis. So we are going to have moment of inertia of the bottom flange about the neutral axis is also going to be BD cubed over 12 because it is also a rectangular section plus its area into YC. Therefore, the distance from G to GB, that distance is going to be given by YC minus Y. Therefore, the compressive section minus Y, and then we got it squared. So that's going to be the breadth of the bottom flange, 120 millimeters, multiplied by its depth, which is 40 millimeters, got it cubed, all over 12, plus the area of the bottom flange, 4,800. Therefore, 4,800 into YC is 158.5 minus Y for the bottom flange is 20. And then we got it squared. Now, that is going to give us the moment of inertia of the bottom flange about the neutral axis being 92,714,800 millimeters raised to 4. Therefore, that is the moment of inertia of the bottom flange about the neutral axis. Now, the moment of inertia of the whole I-beam section about the x-axis or about the neutral axis is going to be the sum of moment of inertia of the top flange plus the moment of inertia of the web plus the moment of inertia of the bottom flange, which is going to give us 2.056 times 10 raised to the power of 8 millimeters raised to the power of 4, which when we convert it to meters raised to 4 is going to be 2.056 times 10 raised to the power of -4 meters raised to 4. Therefore, that is the moment of inertia about the x-axis or about the neutral axis of this I-beam section. Now, after getting the moment of inertia, we are now going back to solve the two equations that we have. The first one is to determine the maximum bending moment. Now, for us to determine the maximum bending moment, we are going to apply the bending equation or the fractional formula, which is given by this relation: M over I is equal to stress all over Y. That is the bending moment divided by the moment of inertia is equal to stress divided by Y. Now, since we want the maximum bending moment, we are going to make M the subject of this relation, and this is going to lead us to a maximum bending moment will be given by the tensile stress. Since we are being told that the tensile stress in the top flange is not going to exceed 40 meganewtons per square millimeter. Therefore, maximum bending moment is equals to tensile stress multiplied by the moment of inertia about the neutral axis of the whole beam section all over YT. That is the section subjected to tensile stress. Therefore, this is going to be tensile stress is 40 meganewtons per square millimeter. We convert that to newtons per square millimeters, and that is going to be 40 times 10 raised to the power of 6. Multiplied that by the moment of inertia above the neutral axis, which is 2.056 times 10 raised to the power of 4 meters raised to 4. Then we divide this by YT, that is the section subjected to tensile stress, and we are going to convert 121.5 millimeters to meters. So that is going to be 121.5 times 10 raised to the power of -3. Therefore, after we have multiplied all that, we are going to have a maximum bending moment of 67,687.2 Newton meter. Now, when we convert this to kilonewton meter, we are going to divide by 1,000, and that is going to give us a maximum bending moment of 67.7, that is to 1 decimal point, kilonewton meter. Therefore, that is the value of the maximum bending moment. Finally, the value of the compressive stress in the bottom flange. Using the same relation, we are going to make stress the subject of this relation, and therefore the compressive stress will be given by the maximum bending moment multiplied by the section subjected to compressive stress, which is YC, and then we divide this by the moment of inertia of the I-beam section about the neutral axis. Therefore, the compressive stress is going to be a maximum bending moment of 67.7 times 10 raised to the power of 3, converting to Newton meter, multiplied by YC. YC is the section subjected to compressive stress, which is 158.5 millimeters. Converting it to meters, we multiply by 10 raised to the power of -3. It's just dividing this one by 1,000. Then all over the moment of inertia about the neutral axis, which in this case is 2.056 times 10 raised to the power of -4. So the compressive stress will be 52.19 times 10 raised to the power of 6 newtons per square meter, which when we convert it to meganewtons per square meter, that is going to be 52.19 meganewtons per square meter. Therefore, ladies and gentlemen, that is how we determine or how we calculate the value of the compressive stress that is subjected on this bottom flange. So we appreciate so much for watching our video. If you have liked it, if you have learned something today, please subscribe to our channel so that whenever we upload a new video, you'll be the first person to be notified. Thank you. See you in our next lesson.